Hello? Okay. So in the middle of the school on quantum computing, actually in the middle of the first week of the school, it's a pleasure today to have Anna Predojević from the University of Stockholm that will give a lecture about quantum dots and their roles in the entanglement and a lot of interesting related facts. Just a little bit of introduction. She graduated from the University of Novi Sad in Serbia, but then she immediately started the tour in Europe, the PhD in University of Barcelona, and then she got a postdoc and then a position in the University of Innsbruck before moving to Ulm, which is a famous place for physicists, and then to Stockholm, where she's coming from now. So, without further ado, please tell us everything about quantum dots.
Thank you very much. Thank you for a lovely and very detailed introduction. As said, I'm going to talk about quantum dots today, and I'm just trying to find a place where I can see you in the slides. It's a little bit small. I will tell you a lot today about quantum dot sources, and as the title says, I'm going to talk about efficiency, about entanglement, and mostly about correlations. So before I start, I should tell you a little bit about quantum dots, if you're not familiar with. And we like quantum dots because they are sources of quantum light. And when you talk about sources of quantum light, and specifically if you are focused on entanglement, then there are two types of sources that you might encounter, and that is spontaneous parametric down conversion and quantum dots. So what is so special that differentiates quantum dot spontaneous parametric down conversion? And I can give you that in these two pictures, and that is the high photon generation probability in sub-Poissonian statistics. Because the process that generates photons in spontaneous parametric down conversion is purely probabilistic. However, quantum dots, what I will show you soon, they are atom-like. So they have discrete energy levels, and you can drive them just like atoms. You can observe Rabi oscillations, you can drive them coherently. And then if you carefully engineer the pulse with which you're driving them, then you can observe also Rabi oscillations. And to back the claim about the high photon generation probability, this is a Rabi oscillation, which is recorded on a bi-exciton photon, our resonantly excited quantum dot. And as you can see here, we can have, at least in this set of data, emission probabilities of nearly 0.9.
Sorry, I'm going to stop you because this colloquium is for a more general audience. I don't know what Rabi oscillation is. What's a Rabi oscillation?
I can also open the slides from the lecture. Okay, it's okay. Rabi oscillation. So when you drive a two-level system, when you drive the atom with the light, then you have a two-level system which is interfering with a very coherent light field. And this coherent interaction can happen in a way that you are giving a photon away from the field for the atom to absorb it, or you can also kick the atom to emit a photon due to the coherent interaction between the field and the atom. So you can see this as an effect of constructive and a destructive interference in the interaction between a classical light field and a laser field with a two-level system. And as you can do this, you can then excite the atom with a very high probability. Depending on how you shape your pulse, so depending on what is the phase between the field and what atom expects to see, you can drive it from zero interaction to the maximum interaction, where you can get the atom to be excited with 100% probability. And when it's excited with 100% probability, then you're going to have also a 100% probability to emit. And therefore, you're going to get very, very high probability to see an emitted photon. Or even if you have, I'm going to show you here, a three-level system, you can have a photon pair. And in essence, the quantum dot then serves as a single photon gun. So you can get a stream of single photons. This is not a case where I said spontaneous parametric down conversion, because there the process is probabilistic. There is certain very, very small probability that some of the photons will down convert, and you're not going to ever observe the Rabi oscillations. What is very important here is that we are driving this with a probability 0.9. So we had something like 80 megahertz rate of photons impinging of this, so 80 megahertz rate of pulses impinging on this quantum dot. So if we exciting it with 0.9 probability, that means that we get 72 million excitations, and that is a lot. So another thing here is this sub-Poissonian statistics. So if you send this light onto a beam splitter and you measure the autocorrelation function, this is what you're going to see. And as you can observe, at 0 delay, there is almost no signal, which means that this is really, if we ignore now that the autocorrelation function has nothing to do with the efficiency of the source, but this is the closest that you can get to a single photon source. How do we create these quantum dots? So they are man-made artificial atoms. So the way to create them is to use two semiconductors, one low, one high band gap, and they need to have their lattice constants to be very similar. So you place several layers of high band gap material, and then few layers of low band gap material. And what is going to happen is that since they have similar lattice constant, they will try to fit in each other's lattices. And then after a few layers of the material that has higher lattice constant, is going to start to bulge, and it's going to form these little islands that you can see here. What you can see here is a transmission electron microscopy of a quantum dot. With this is an indium arsenide as a low band gap, and gallium arsenide high band gap material. And this is the same little island that you can observe here. Later, you cap it again with gallium arsenide. So what is interesting about these little islands is that they are strain deformations. When you have a strain deformation in a semiconductor, what is going to happen is that you're going to change the electronic landscape. And at the places where you have these quantum dots to form, you're going to get a little potential well. And these potential wells, they are comparable with the de Broglie wavelength of the electrons and the holes in the surrounding semiconductor material. And therefore, these electrons and holes can be trapped in discrete energy levels of a quantum dot. What does that mean? That means that you can have, for example, formed electron-hole pairs, which then, when they recombine, they will give rise to emission of a single photon. Or you can have, for example, trapped two electron-hole pairs that will combine, and they will recombine in a cascade, and they will give rise to emission of a photon pair. This specific configuration here, you can also see, as I said, as a tree-level system. And this is a very interesting system for us because we can generate entangled photon pairs. So here what we have is the ground state. This is the so-called exciton state, or a single electron-hole pair that are trapped in the quantum dot potential. And if we have two electron-hole pairs, then we have this level here that is called the bi-exciton. It's a tree-level system. And similarly to the original space experiment, what you can get is a decay. It's a cascade decay. In this case, these photons decaying, I labeled them here in yellow and in green. They have opposite but linear polarizations. So if we would not have this splitting here, which is called fine structure splitting, and I label it here with S, if we wouldn't have it, and these two levels are degenerate, then it was the process of decay also becomes degenerate, which means that without measuring the polarization, you cannot tell which of the two decays have actually happened. And by default, you get polarization entangled photon pairs. However, what is the case with quantum dots? There is a specific asymmetry in the formation of quantum dots, because as I said before, they are generated through strain, and when they're generated strain, they do not get exactly the round shape. So you have this splitting of the exciton levels, which is called the fine structure splitting. And in principle, if you would like to experimentally show that there is a polarization entanglement in quantum dots, you need to eliminate the splitting. this is not the only way how you can generate entanglement in quantum dots. You can use, for example, the time energy entanglement, which has its origin in the seminal paper by Franson. It's a many years old paper, which says that if you have a probability amplitude to excite a system at, for example, 2 different times, and then you get these probability amplitudes to interfere, you will also create a condition to observe the violation of Bell inequality. And this is the basis for so-called time bin and the time energy entanglement, which is simply just another way how to, another degree of freedom, how you can achieve entanglement. We mostly work with the time bin entanglement, and you can ask me later a bit more about the technical details of that, but we mostly work with interferometers, because as I said, you need to have 2 different times at which you have certain probability amplitude, which you will create by letting your laser excitation to go through an interferometer. But later on, you also need to interfere this probability amplitude. For that, you will again need an interferometer. But for technical details, if you like, you can ask me after the lecture. What I would like to talk about today are 3 topics. And I think that all 3 of them they're very different, but they are very interesting in themselves. The first one is about the devices, and it's more related toward the growth and toward the fabrication of the devices. While the second 2 are studying the light that we emit, that we get to be emitted from such devices. So what you can observe here is a typical spectrum of what you get when you excite your quantum dot resonantly, but you excite it to the bi-exciton state, which is this second excited state in the 3-level system. Your system will decay from the bi-exciton to the exciton to the ground state, and will emit you the bi-exciton and the exciton photon. These 2 photons, they do not have the same energy, because when you have an electron-hole pair, they have a Coulomb interaction between them. So therefore, when the first electron-hole pair recombines, there is going to be a shift in energy. And therefore, these 2 photons emitted from a quantum dot, they will never have the same energy. They're usually something like 2 nanometers away, which is, in a sense, very favorable, because we can place a laser to excite the quantum dot exactly halfway between the exciton and the bi-exciton, and then drive this transition as a 2-level process, which means that the energy, when we take 2 photons from the ground to the higher excited state, will match the resonant transition. What I wanted also you to observe here is the difference between the wavelengths, because one of the problems with working with quantum dots is it's great. You can have these Rabi oscillations. You can generate a large number of photons, single photons or photon pairs. But then how do you get to have these photons to go into your detection system? Because quantum dots, they emit in full solid angle. So even if you put a large numerical aperture lens, you're going to get a very small proportion, a very small percentage of the photons to be emitted toward your detection. So what is usually done to mitigate this is you need to place the quantum dots in some sort of photonic environment. So for those that were at school, they've seen a lot of waveguides and a lot of ways to manipulate the photons, their emission and their collection. So we do something similar. We are placing quantum dots in engineered photonic environment. And what I can show you here as an examples are, for example, nanowires, bullseyes, various types of cavities. But what is problematic about collecting both exciton and a bi-exciton photon is that you need to find a solution which is broadband. And finding a broadband solution is not so easy as you would imagine. So if you have read ever a paper about quantum dots, and you probably did because quantum dots are used in many experiments that deal with single photons. For example, a lot of experiments with boson sampling or photonic circuits, they will use quantum dots, and those quantum dots will be embedded in microcavities. However, usually the microcavities are made with a moderate Q factor, which means that those are relatively good cavities. They have quite narrow line width. And this is done because you would like to exploit one process that happens in such type of cavities, and that is a Purcell factor. A Purcell factor allows you to collect a lot of light emitted from a quantum dot along the axis of the cavity, and then you can get the collection efficiencies of 70, 80, 90%, which is very, very good. However, this doesn't really work if you want to collect pairs. Why so? Because in order to collect the pairs, you would need to relax this condition for the line width. And your cavities will start to be broader. When they start to be broader, then you will start to reduce the Q factor, and you will start to lose the Purcell factor. And if you talk with people that make cavities like this, they say, well, the moment that you lose the Purcell factor, you will stop collecting so much of the photons because there's not going to be something to drive them out. However, this is not absolutely true. So this is equation that shows us something that's called the beta factor. The beta factor is probably the best known for those that are manufacturing diode lasers. And it's a ratio between all the light that is generated and the light that, it's a ratio between the light that you collect with your device and all the light that has been generated. So if you have a beta factor of 1, that means that you have built a device that can collect all the light that you have generated. And commonly, when we talk about microcavities, you will see this equation, but this term here will be equal to 1. And then it's easily seen. If you do not have any Purcell effect, which means if the Purcell effect is 1, there's no enhancement, then you cannot get a larger beta factor than 50%. However, this term here, which is physically relevant and very often forgotten, says, well, it's not only about how much you collect with the device, it is also the light that you do not let be collected because it's not resonant to your cavity. So we wanted to explore this effect, and we deliberately made microcavities that did not have this high quality factors I show you. So they had quality factors between 200 and 300. Line widths that were much larger, something like 4.5 nanometers, so to be able to collect both exciton and the bi-exciton. And we were also varying the pillar diameters. For those that are interested in growth, we could place these pillars with the accuracy of nearly 30 nanometers over the site of the formation of quantum dots, but these are technicalities. So let me show you what we see. Well, we first did the theoretical modeling, and we looked at this beta factor as a function of the diameter of the pillar. And as you can see, there is an oscillation, and I will explain you in a moment what is happening. So up there, we see this is the pillar diameter. This here black line is the cavity mode. And what we see here is what I'm going to call the side mode. So the cavity mode is the light that you collect along the pillar. And the side mode is what will go in other directions. So when we now start to change the pillar diameter, you will see that we have this side mode forming itself at specific diameters. You can see this process as a beam splitter, as interference, because you set certain set of conditions, and all of your light will go exactly in this black mode, which is the cavity mode, but with a certain other set of conditions, which is determined by the size of the micropillar, you will get most of your light to be emitted in this side mode. And we can see this also in this graph. This 1.65 micron pillar is this point here, which has a very small beta. But if we start to increase again the pillar diameter, you will see that somewhere around 75, we again have very high beta factor. And this is again due to the interference conditions that are going to attenuate this, or distractively act on this red mode and enhance you the black mode. Having said this, we have done then also a lot of measurements to characterize how much light we get out. And we have taken all of the experimental parameters in account. We got a collection efficiency of something like 70%. What does this mean? This is one of the 3 best results that has ever shown in this field. And also, we've learned if we tweak a little bit the environment, change the substrate, change the number of layers in the cavity, we can also even get up to more than 80%.
How do you distinguish if it's 1 photon or 2 photons that are being emitted?
In the cascade, or so in the cascade, microphone.
Should I repeat? Yes. How can you distinguish whether you emitted 1 or 2 photons in this experiment?
Okay, so if it is like if we have a bi-exciton cascade or a single cascade, well, if we drive the system, let me go back to one graph here. We drive this system with a laser from ground to the bi-exciton state using a 2-photon process. And once we do this, then majority we are driving coherently from ground to the bi-exciton state. And if we are careful how you design your pulse, you will mostly drive exactly that thing. So ground, bi-exciton, and then you're going to have a cascade. Of course, sometimes it can happen. There's a small, very small, but not 0 probability that you're going to drive the system directly from the ground to the exciton state, but if you carefully tailor the pulse and you're careful how you do the excitation, this is going to be minimal. This is going to maybe be 1 to 3% maximum.
And the photons have the same energy always in the bi-exciton?
Yes. So bi-exciton always have a same for a specific quantum dot. Different quantum dot grown on another wafer is going to have different energy. But once you have a formed quantum dot, the bi-exciton is always at the same energy, and the exciton is always at the same energy.
And you detect photon by photon, you have photon what is the photon detection?
Avalanche photodiodes. And for example, to your question, this is a spectrum. This spectrum is going to be same every morning from day to day. It's not going to change. Okay. Having said this, let me go to one tiny little bit different topic. And this is related to the 2-photon interference. 2-photon interference is, well, I find it to be a very magical process. Because what is happening here, if you have 2 photons, 2 indistinguishable photons on a beam splitter, they will always exit down the same port. This is also known as a Hongo-Mandel interference. And it is the basis of everything that you do with the photons, because there is no photonic circuit that is going to work without 2-photon interference or a Bell measurement or anything that you like, because the Hongo-Mandel interference is the only known way how the photons interact. So you need 2 photons, you need a beam splitter. If you now place your detectors here at the output of the beam splitters and decide to write the correlation function, you will learn that it has this form, where here we can talk about the intensities or the photon number at the time t or the t plus tau. And here we can talk about the first order coherence. And if I a little bit simplify this and say, okay, photon 1 and 2 are identical, so I don't need these indexes, then you're going to get an expression like this, which already tells you that if you would like to get this function to be 0, then you need to have photons that are having a Fourier that are in a Fourier transform limit, that their G1 is, shall I say, matching their lifetime. And this is an experiment that is very often exploited. It's not only about quantum dots, it's about the NV sets, it's about any single photon emitter where you would like to learn about the lifetime, about the coherence, about the ratio, and if the photons that will be emitted by such a source will show you this Hongo-Mandel interference. And usually, the way how this experiment is performed is you would excite your quantum dot. And as I said, it could also be an atom or NV center or any quantum emitter. And then you will excite it with 2 consecutive pulses. And then you will have, most of the time, emitted a photon in each of these pulses. Then you will send this light through an interferometer, and the delay of this interferometer be equal to the delay that you have between these pulses. And then here, you will have a number of events where you will have 2 photons that are impinging on a beam splitter, and you can observe the Hongo-Mandel interference. If you decide to make your photons distinguishable, which is easy, you just need to put a polarizer in one of the 2 paths, then you're going to get a picture like this, and you can do this as an exercise. You will see that if you have an interferometer, you will get at the end 5 peaks. But the interesting one for us is this one in the center. If you have opposite polarization of the photons, these photons will be distinguishable. They will not show the interference. And you will have here formed a peak coming from coincidences between the detector 1 and the detector 2. However, if you have equal polarizations, then the Hongo-Mandel interference will happen, and you will not have nearly, well, here in this experiment there was a little bit, but in general you should not have the signal here because your photons are bunching to one or the other port of the beam splitter, and you simply do not have the coincidences. This is how this experiment works, if it works, and I think this example is very nice. However, things start to be a little bit different. I think that the theorists will appreciate this because you like your cells.
They're free. Can you completely ignore QED, electrodynamic effects? Or?
Well, you know, you cannot fully, but you need to be aware of them. So you need to know what is exactly happening in your source. If you have it in, you know, if it's a cavity source, you need to take into account all of this and see how they affect your photon.
But they're negligible.
But most of the time are negligible. Sometimes not, but most of the time negligible. Because most of the time you do not try to make the cavity even with higher Q factor, where you would then really observe avoided crossing and stuff like that.
Sorry, I have a question here.
Yes?
So when the 2 photons have the same polarization,
yes.
Actually, what is different in the experiment with having just 1 photon interfering?
With itself?
Yeah.
Well, in that case, you're just going to do an autocorrelation function, which is where you will have only information about the intensity, because you don't have interference. There is no, phase doesn't play the role in that experiment.
So the 2 photons can have different phases?
So the 2 photons can have different phases. So the photon, so if you're referring to Hongo-Mandel interference as 2 photons impinging on a beam splitter versus an experiment that's just 1 photon impinging on a beam splitter. So this first experiment is a Hanbury-Brown and Twiss experiment, which is also going to have as an outcome a correlation function, a so-called autocorrelation function, and we have them on the first, have it on the first slide. This one. This is an experiment, a single photon on a beam splitter, and the only thing that we can learn from this experiment is do we have a quantum or classical light? Is it bunching or anti-bunching, or is its value is below, shall I say, normalized function, which means that we have a sub-Poissonian light. This is the only thing that we can learn from that measurement. The other type of measurement that I show you with 2 photons on the beam splitter, this is a bit more, for me at least, a bit more interesting experiment, because we're going to get not only information about the intensity, but also about the G1, which is related exactly to this formula here, because just this G1 is important for us here. What I wanted to say here is that I showed you this Hongo-Mandel experiment, but I also want to show you that things change a little bit depending what is your source of photons. So this experiment that I showed you in the previous slide, this is a 2-level system. 2-level system is a quantum dot. We drive just an exciton, and you have a 2-level system, and you're interfering the photons. However, what you have here as a three-level system is if we look at the bi-exciton emission time and the exciton emission time, you see this triangular shape, which is a print of a cascade emission, because you cannot have an exciton before you have had a bi-exciton. And then if you write a joint function for this decay, you're going to get something like this. And with a little bit of math, you will learn that this is not separable state. It's an entangled state. What we have here as these gammas are the decays of the bi-exciton and the exciton. And here in T's are the emission times. So this here Heaviside step function tells us about the ordering of the photons, saying you can only have an exciton after you had a bi-exciton. And when you take a little bit closer look at the state of the, for example, exciton, you can write the same thing for a bi-exciton, you will learn that the purity of each of these individual photons does not need to be 1, and that the purity will be determined by the ratio of the lifetimes. And so now, when you have a photon, sorry, when you have a emitter where the photons do not have a high purity, this affects your hongomondal interference. Because we're not talking anymore about here is a very pure state single photon, and here is a very pure state single photon, they're going to do hongomondal interference. You're going to have problems with that. And we have studied this case. So I have to say here, due to the fact that we have here decay times, we needed to pick an emitter with the specific decay times. Otherwise, the analysis would start to have too many parameters. So we picked a specific emitter which had these lifetimes that allowed us then to determine what is the purity of the photon and how much this purity is affected by this cascaded decay. And we looked at this, and we calculated, again, the correlation function and wanted to see what is exactly do we get at the output of a beam splitter. So this is what we get. Let me just go 2 slides back. So I'm talking now only about this middle peak here, where we observe or we do not observe the hongomondal interference. The intensity peak here, or here, I have normalized them. You can ask me later why I decided to normalize it like this. It's very, very technical. Are telling us effectively the same piece of information as this peak here. And that is what would happen if we had opposite polarizations. What is going to happen if we do not have a hongomondal effect whatsoever. Here we have the G1 that tells us about the coherence length. And when we subtract them, then we get this autocorrelation function that tells us how good our hongomondal effect is going to be. And as you can see, we have some residual intensity here, which means that the hongomondal interference is not going to happen so ideally as if you have 2 pure states impinging on a beam splitter. But you're going to have reduced visibility. You will have some probability to have a click on both ports. And this is caused specifically by this time ordering between the bi-exciton and the exciton photon. Of course, if you now decide to make an experiment, and this is what we did. So these are our experimental results, which is now the middle peak and the 2 side peaks. You will learn, because, I'll explain why. You will learn that the probability to see output on both, to see a click on both outputs of a beam splitter is considerable. It's much than this 15% that we have calculated. It's around 37%. And that is a general problem of every artificial device, everything that is happening in a semiconductor. In semiconductor, you will have also a lot of decoherence. So you will have an interaction of your quantum dot with all sorts of phonons in its environment. Many things can change, and you generally do not have these levels to be very, very stable. So after some time, these levels will start to shift, and this is going to affect exactly this G1 part of your equation that you're going to start to lose the coherence. So this is a very interesting decoherence because there are many ways how you can measure decoherence of quantum dot levels. There are many methods of interference, of some sort of spectroscopy, of several waves mixing. But the interference that we are talking about here is, sorry, not the interference, the decoherence that we talk about here is the decoherence that you see in the wave packet that is emitted. And for that is a little bit different, and it's very interesting, and it's the only one that is relevant for the Hongo-Mandel interference. Because you can have different measures of how coherent your exciton or your biexciton are. That doesn't mean that this is going to directly translate in a graph like this. So we have studied this. We studied this theoretically and experimentally. So this is our experimental result. And we studied this with Celso using the sensor method. And the sensor method was saying, in very simple words, you have your three-level system. You want to describe your three-level system writing your master equation, you write your Lindblad terms, and whatever you would like, you find in a textbook to describe your three-level system. But then you add this to the Hamiltonian, and that would be two weakly coupled photon modes that can allow you to learn about the emission of the exciton and the biexciton. And then having them here, you can learn a lot about the correlation between these modes, and you can learn a lot about the correlation between the emitted photons. And taking this, adding this additional Lindblad term to the master equation, we can plot what we expect to see in our experiments. And since it's a Lindblad, it's a master equation, and the Lindblad terms can include also the decoherence, then you can also put the decoherence you would like to put inside. And then you can model this for any decoherence that comes to your mind. And then you can compare this result to your experiment. And from it, you can learn what is the coherence. Of course, I have to point out that this is our theoretical model, but in order to compare it with the experiment, you need to convolute it with the detector responses. So because we don't have a very, our detectors do not have a resolution of a delta function, of course. I mean, we have something there, and when we match it, you can see that this matches very nicely. You can, of course, do then a graph for any different coherence length. And this is probably one thing that I would like to show the most. So this is a measurement of this middle peak performed with a very, very good detectors. So where the resolution is really, really good. It's below 16 picoseconds. And you can see even the signs of the dip. And what we did, we started from 4.8 Kelvin on a quantum dot, and we started to warm it up. So we have let all of these bad things in semiconductor happen and start to destroy the coherence. And how we were destroying the coherence, you can see how our Hongo-Mandel interference was also getting worse and worse, and how you get more and more probability to see the clicks on different outputs of a beam splitter. So I guess I still have 10 minutes, right? Okay, let me do one more topic. I work on many different things. So when for me to pick which topic I'm going to talk about, it's like telling me, okay, which finger you want to cut off. So, okay. But they're usually very different topics, but it's fun. Okay, it's about non-Gaussian states. So I do not know how much you know about the Gaussian, non-Gaussian states, but in general, you will find a definition that the Gaussian state can be made by any combination of a displacement and squeezing operator. And what is a typical thing about the Gaussian states is when you write their Wigner function is going to be positive. But there is a class of states that are very interesting, so-called non-Gaussian states, that are characterized by this negative Wigner function. And I'm not going to go too much into detail. The Wigner function can be reconstructed, it can be measured, but there's a little bit of a problem with characterizing non-Gaussian states by measuring the Wigner function, is that it is extremely sensitive to losses and noise. Because at the moment where you have 50% of vacuum in your state, this state is more a Gaussian state, a vacuum state, than a non-Gaussian state. And therefore, due to the optical losses in experiments, it's very, very hard to characterize non-Gaussian states, optical non-Gaussian states. This is a difficult measure. If you want to learn about states, you can do something simple. You can do this autocorrelation measurement, but this will just tell you if it's Poissonian, sub-Poissonian, so it's not really a good measure. It is insensitive completely to losses, but whatever. And now what we were for years wondering is, if you now start from a very pure single photon state and now decide to attenuate it to completely having a vacuum state, which path do you take? What kind of states you will encounter on the way? So we decided to say that we have states where you can measure a negative Wigner function. So those are the states that must not have more than 50% of losses. Then quantum non-Gaussian states, non-classical, and any other. You know, we were open-minded and said, okay, maybe there is something more than that. And I was mostly here interested in this quantum non-Gaussian state. A quantum non-Gaussian state is something, we call it we call in that way a non-Gaussian state that usually you would not be able to detect if you try to reconstruct the Wigner function because you have too much losses. So you need to recur to certain tricks to be able to detect your non-Gaussianity in a state. And one of the tricks is try to extract the non-Gaussianity out of the statistics. So there's a lot of derivation details here that I do not want to put. I just wanted to give you an idea of these non-Gaussianity criterions. And most of them, specifically for single photon or pair sources, are dealing with these quantities, which is the probability of 2 photons or probability of 1 photon, which you can measure, measuring the photon statistics. And in this specific case, we have also introduced eta, which is the transmission of the lossy channel. And to kind of give a spoiler alert, what we managed to do here, we have found a way to measure, to detect non-Gaussian properties of a state by simply using these statistics, but also being able to account for losses, which is very important because any other method, like either the Wigner function or anything else that you can come up, will never be able to account for losses. And the measurement is relatively simple. It is based on measuring the success events. So we have the bi-exciton, the exciton, and the success event is when we have a cascade. We have 2 photons coming, the bi-exciton and the exciton, and this is what we want to see, a photon pair. But we put also each of these signals on a beam splitter. So we are looking how much this 2-photon contribution is, how much noise we can see in the signal. And then we compare it to this criterion. Of course, there are a lot of technicalities. How do you do this in experiment? Because you need to be able to accurately determine the probability of success and the probability of error, which means that you need to be very careful to find the true rate of your source, to find the true rate of these double clicks on each of the pairs of the detectors. So for those that are interested in this, we did a few tricks here. For example, we have used Ramsey interference to determine where exactly we drive our quantum dot with a 50% probability, to pin exactly at which power. So instead of, let me compare this for a second with this. Now I need to scroll over back with the Rabi oscillations. If you measure Rabi oscillations and you do a good fit, you can also determine from the fit what is the probability with which you're generating photons. But as you can see here, it's not a very nice Rabi oscillation. Rabi oscillations, when you see in a textbook, they really look like a sine function. They go up and down, and you can many flips. When you work with semiconductor materials, very often when you start to apply a lot of power, you start to heat it up. You start to create the decoherence, and things simply do not work. However, if you apply a Ramsey measurement, you can learn where exactly 0.5 is, and you don't need to go further. You say, okay, I'm going to go to 0.5, and I know that now if I have 80 megahertz laser, it's 40 megahertz with which I am driving my source. We looked at that. We've looked at the autocorrelation, the so-called blinking. That also is another process that reduces your efficiency of excitation. And we also looked at the losses. And we learned that these are true probabilities for success and for the error. And then we compared it to the criterion. Here in the red, you can see the criterion. And here is the point that we have measured. And of course, now we can, since we have this eta in the equation, we can simulate losses. And then we can say, okay, now if I would take this source and I will put it in a very, very long optical fiber, and I would send it from my city to your city, will the state still be non-Gaussian? Well, it depends on the losses. So what we did, we simulated the losses, and then we learned how bad we can treat the light, so how much losses we can afford to give to the state, and still at certain points stay on the right side of the criterion. Which is, I think, very important if you would like to characterize, nearly done. If you would like to characterize your source in some distributed network, if you would like to understand how resilient it is to noise. Of course, we did this for coincidences. We can also do this for single photons, so just one of the two, and also find the experimental point and look where it cuts the criterion. For single photons, we've learned that you can even attenuate it to nearly 7.5 dBs, and you will still be able to see the non-Gaussianity in this signal. And this might be just a number, but for an experimentalist, this is quite a bit of attenuation. So you can lose a lot, and you still be able to tell it is a non-Gaussian state. So here I am at the end of my talk. So what I've showed to you here were three very, very different things. So one was a step into engineering, into how the sources are made. What I wanted to point out about this source is these are low Q cavities. So we got a very high extraction of the photons from low Q cavities. And those are cavities that do not have many dBrs. The process to make these cavities is a very simple lithography. So this is a method which is compatible with every continent. You do not need to have a very, very, very expensive clean room and make very, very delicate structures. Such low Q cavities are really, really easy to fabricate. I also show you a framework in which you can learn about the coherences of quantum dots. You can actually, through a Hongo model measure, access the coherence, the one that affects the Hongo model measurements and the coherence of the emitted photons. And since you have access to this information, then you can try to change the design of your quantum dots, explore cavity QED, or whatever other method you have to increase the contrast of your Hongo model. And I have shown you a little bit about this text of non-Gaussianity, which I find to be very interesting, and they are a little bit more, shall I say, experiments-oriented, but are a very nice way to learn about the states that you create in the lab. And the last, this is marketing for Miroslav's talk, so it's about deep learning to learn about the entanglement. This is a little bit more of marketing. Please follow us. We're doing a very big outreach event, so you can follow us on LinkedIn and see how we are celebrating the year of quantum in Europe by shifting one of these quantum dot sources from one lab to another for a whole year through 12 different labs and making all measurements on a single source. And at the end, of course, they haven't done this single-handedly. There were a lot of people that have paid for what we do, and there's a lot of people that have worked on what I presented. And thank you very much for your attention. And please, if you have questions.
Questions?
How do you measure the photons?
How?
How do you measure the photons?
So you have two ways to detect them. The simple one is simply to look at them on a very cooled CCD camera, which is sensitive to single photons. And that's where you can get the spectra, as the one that I showed you. To count them, you're going to use the avalanche photodiodes.
Thanks for the talk. It was really interesting. I have two questions. The first one is there a maximally non-Gaussian state?
How you would call maximally non-Gaussian?
I've encountered some measures for the non-Gaussianity of states that they are related.
You have some measure. You can measure, for example, I don't know, the dip of the negative side of the Wigner function. So I wouldn't know how you cannot really have a maximal one because I don't know how I would define it, but you can characterize, you can quantify how non-Gaussian your state is if you can measure the Wigner function.
Yes.
And in this case of these criteria, you will simply look at how many standard deviations you are from the criterion.
Okay. Have you ever encountered a maximum value for the negativity of a Wigner function?
So I personally have measured negative Wigner function, but many years ago when I was a student. Here we do not deal with the negativity of the Wigner function because we simply never have the efficiency above 50%. Because I showed you that we get these photons out already with 60–70%, but then you also need to account the propagation, then the detector, then if you want to measure the Wigner function, then you need to overlap it with your local oscillator. That one doesn't need to be necessarily 100%. So for us, it would be impossible to measure the negativity of the Wigner function. And not only for us, it's not an easy thing to measure, to put it that way.
Thank you very much. And then the second question is there a way to generate non-Gaussian states from light matter systems?
From, sorry?
Light matter systems. Like.
Yes. We can discuss this. This is a little bit more intricate topic.
The naive question, if nobody has a question. So you had different paths coming from the non-Gaussian to ordinary states, right?
Yes.
I didn't really understand.
This one.
Classical paths? No, I think it was before that one. No, before that. Yeah, that.
Yes.
Right. So these are classical paths, this A, B, C, D. I just didn't understand what it means.
So we wanted this as an illustration of saying, okay, I know what is a pure single photon state. I know that. I also know what is a vacuum state. Yes. But what happens in between? What happens when I start to add the noise? Am I going to just go straight line from 0 to 1? Or am I going to go through a different class of states? Because, for example, the green one here are non-classical. So there's the states where you're simply going to see a sub-Poissonian distribution if you measure the autocorrelation. I mean, all of these are non-classical, but here are quantum non-Gaussian, and these are going to have a negativity of a Wigner function. So they're not separate, but they include each other. So.
But they can't tunnel from one to the other? It's really a classic. It looks like some classical process. Couldn't it just tunnel from A to D without going through B and C? Or?
From A to D?
Yeah.
No.
So it's not a quantum mechanical process.
No, because there's a trick here with the C. is actually all of this.
I see.
The B is all of this, and A. So the states that have negative Wigner function, they are, of course, non-classical states. It's just that the ones that are here, for example, they are non-classical, but they might have all the non-Gaussian properties, but I cannot detect it with the negativity of the Wigner function because I need different amount of vacuum in the state.
Okay, thanks.
Going once, going twice. Oh, so we can thank Anna again.